Alright, let's get started with Lesson 8, Boiling and Melting Points. In this lecture video, we're going to focus on the important factors that determine the melting and boiling points of compounds and molecules. So, to begin with, let's look at some basic ideas between intermolecular forces and chemical bonds themselves, and how chemical bonds and intermolecular forces influence the melting and boiling points. So, many properties of liquids, including their boiling points, reflect the strengths of the intermolecular forces. Similarly, the melting points of solids increase as the strength of the intermolecular forces increase. As shown in the table below in your notes, the boiling and melting points of substances in which the particles are held together by chemical bonds tend to be much higher than those substances in which the particles are held together by intermolecular forces. So essentially what we're saying here is that it appears that the chemical bonding has a stronger influence on the boiling points and melting points of compounds than intermolecular forces do. And we can see that very clearly in this table. So let's take a look at chemical bonds. All right, we have covalent, ionic, and metallic bonding that's occurring. So we have lithium fluoride that is represented by ionic bonding, and beryllium will be our representative of metallic bonding, and then diamonds we're going to use for our covalent bonding. Now, this covalent bonding is a little bit different than the type of covalent bonding that we've looked at before. The covalent bonding that's occurring in a diamond is forming a large crystal structure. A lot of times we call it a crystal lattice structure with covalent bonding nature. We saw crystal lattice structures with ionic bonds, but so can covalent bonds form these lattice structures. And so a diamond really essentially is more of a covalent network. In fact, I would write that word down, network, a covalent network, than it is really a molecule. Okay? So other covalent networks that exist are like sand, like silicon dioxide. In fact, there's a lot of silicone elements that are in these kind of compounds form these network structures. Carbon is notorious for forming covalent network structures. All right, so don't really think of them as molecules, more as solid, big crystal structures, as diamonds go. So let's take a look at the general trend of boiling points and melting points. As you can see, the boiling point seems to be getting higher as we go from ionic to metallic to covalent bonded networks. And that's typically going to be the general trend that we'll see throughout nature, is that covalent bonded networks, these crystal structures with covalent bonds in them, are super strong. And therefore they're going to have high boiling points. It's going to be very hard to boil and melt diamonds, and you can also see the melting points also increase with that. So in general, the general trend, what I want you to walk away is that ionic bonding crystals are going to have, solid crystals are going to have pretty high melting or boiling and melting points. Metallic bonds are going to be even higher in their melting and boiling points due to the strong nature of that bond. And then these covalent networks will be the absolute highest in their boiling and melting point nature. All right? So now let's turn to the intermolecular forces. Now remember, intermolecular forces govern molecules. So up above these are not molecules that we're talking about. We're going to talk about molecules now. And we already know that molecules, there are three different types of intermolecular forces: dispersion, dipole-dipole, and hydrogen bonding. All right. Now, from our diagram here, we can see that as we move from dispersion forces to hydrogen bonding, the boiling point goes up, so do these melting points. And we're going to look closely at what influences the boiling points for these intermolecular forces in just a moment. All right. But generally, comparing covalent bond networks and metallic bonds and ionic bonds, clearly the melting and boiling points are much higher than what we see for molecules that are only governed by intermolecular forces. All right, and so those are pretty important comparisons to look at here. All right, so let's take a look at molecules only now. Okay, for the rest of this lecture video, that's what we're going to focus on, is just molecules and the intermolecular forces that influence these molecules, boiling and melting points, and maybe other factors too here. So let's look at the halogens and the noble gases to begin with. So start with the halogens. Here are the halogens here. Remember, the halogens are diatomic in nature. So we have F2, Cl2, Br2, and I2. And what do we notice about the molecular weights here? So as we typically go from fluorine to iodine, the molecular weight increases. So compared to that to the boiling point, we see a general trend that as the molecular weight increases, so does the boiling point. Now we can also look at the noble gases. Is that the same? We go from helium down to krypton, we see that the molecular weight increases, and again we see so does the boiling point. So there seems to be a correlation between the molecular weight of a molecule and its boiling point. As the molecular weight increases, so does the boiling point. And this is a true idea. However, it's not just because the molecular weight's increasing. What's really happening here, and this is what I would write down in your notes, is that as the molecular weight increases, so does the dispersion forces. The dispersion forces on these molecules increases. And the more dispersion forces there are in these molecules, then the greater the boiling point is going to be. And so that's a pretty important factor. And so when you're looking at two different molecules, make sure you look at the molecular weight first. If you see that which one has a higher molecular weight, you know that the one that has the highest molecular weight is going to have the higher boiling point in most cases. All right? We'll get more in depth in this in a minute. All right? All right, so here in summary then, the dispersion forces tend to increase in strength with increasing molecular weight. We can see this in the boiling points of the halogens and noble gases, which we just looked at, where dispersion forces are the only intermolecular forces at work. In both families, the molecular weight increases on moving down the periodic table, and the higher molecular weight translates into increased dispersion forces, which in turn leads to increased boiling points. All right. Now, and I do want to comment that all of these compounds that we just looked at, or molecules that we look at, the halogens and the noble gases, are just molecules. All right, and so they're nonpolar molecules. So dispersion forces is all they're going to have. All right, so we can see this again. We have some special organic molecules here, and you don't need to really worry about their names, but the idea here is that here's the molecular formula here, and you can see that the molecule, as we're going down from methane to decane, that the molecule is increasing. It's getting bigger, in other words. And that correlates to an increase in molecular weight then. And you'll see, therefore, as we should be able to predict, the boiling points of these molecules are going up as the molecular weight is going up, and again, due to the number of dispersion forces. Methane has a lot less dispersion forces than decane does. All right? So hopefully you kind of get this idea. All right, now there's another factor besides molecular weight or dispersion forces here that influences the boiling and melting points. The shape, the molecular shape, is also an important factor. So the molecular shape also influences the strength of the dispersion forces. Generally, the strength of the dispersion forces increase with increasing surface area. The more surface area that is exposed on the molecule, the greater the dispersion forces, in other words, are. For example, if you have two molecules that have relatively the same molecular weights, then the molecule with the largest surface area in contact between molecules will essentially have the largest boiling point. Let's look at this with a diagram. So the top one here, we see methane, ethane, propane, and butane, and the molecular weight is increasing in this direction, as you can see by here, molecular weight in grams per moles, right? And then down at the bottom is their boiling point, right? So because the molecular weight increases, so does the boiling point, all right? We got that down. But what about the shape of the molecules? So down below we have two different organic molecules, all right? They have relatively the same molecular weights. They both have 72 grams per mole, but their shapes are different, all right? And if you look closely at, or if you look at their boiling points, and I'll circle their boiling points here, 2,2-dimethylpropane has a boiling point of 9.5 degrees C, whereas pentane has a boiling point at 36.1 degrees C. So why does pentane have a larger boiling point? Well, it's because there's more surface area here. Pentane has a lot more surface area exposed to. So there's going to be more dispersion forces between these molecules. A lot more, okay? Here in the 2,2-dimethylpropane, the dispersion forces are not too many between those molecules. A lot less dispersion forces because there's less surface area, so therefore not as high as a boiling point, or those dispersion forces aren't as strong on those molecules. All right, so we can't just look at molecular weight, we also have to look at the shape of the molecules. And so that's why it's important that you're able to take a Lewis dot structure and be able to draw it and determine the shape of that molecule to give you an indication of how the shape plays into their boiling points a little bit more. All right, so we're going to now turn our focus a little bit more to polar molecules. We have really studied nonpolar molecules and the dispersion forces that affect the boiling points here, but what about polar molecules? Now, polar molecules are going to have permanent dipoles, and so their permanent dipoles lead us to either dipole-dipole forces or hydrogen bonding that occurs. And don't forget, though, that even polar molecules have dispersion forces. And those dispersion forces in polar molecules are going to be absolutely critical. But let's say that you have some molecules that are polar, and they have pretty even molecular weights. Their molecular weights are essentially the same, in other words, okay? Let's do a comparison. So first of all, I'm going to actually draw some structures. So I'm going to draw the structure of propane first. So propane is going to have some hydrogens attached to a carbon. Let me see if I can actually draw this a little bit better. Give us more room. So carbon, hydrogen, hydrogen, and another hydrogen, another carbon, and another carbon, and these are all going to be saturated with hydrogens all the way around. And this is our propane. Now, essentially, if you look at propane, it's made up of a bunch of tetrahedral structures, and essentially propane is nonpolar. All right, so nonpolar. So since it's nonpolar, the forces that are intermolecular forces that are influenced here are going to be just dispersion forces only. So that tells us that the boiling point of propane is influenced only by the dispersion forces. All right, so let's look at dimethyl ether. So that's going to essentially have, make it a little bit smaller, C, H, 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 and then we have an O in the middle, and then a C, H, H, and H, okay? Now there are some lone pairs on this oxygen, and those lone pairs are going to make this a bent molecule. So this is actually going to be polar. All right? It's going to be polar. By the way, this micro right here, down there indicates the strength of the dipole, or how big the dipole is. So for propane, you can see that the dipole is only 0.1, whereas dimethyl ether, the dipole is 1.3. So it's much greater because we're going from a nonpolar to a polar. All right. And then let's look at the next one here, which is going to be, let's see if I can kind of squeeze this in, CH, H, H, and then C, double bond, H, like this. So that's what this is going to be looking like, this aldehyde. And it is going to also be polar. And the dipole is much bigger, so it's actually getting more polar so far. And then the last one we're going to look at here is going to essentially be CH. Let me reset, make that a little bit. CH, H, H, and then we're going to have this nitrogen double bonded here, lone pairs on it. Okay, and this, of course, is also going to be polar as well. All right, and indicating the dipole is getting bigger. All right, so let's kind of look at this. I'm going to draw an arrow here going in this direction here. So looking at these molecules, the dipole is simply getting bigger as we're moving from propane over to acetone nitrile. Okay, and so also I want you to notice, this is really important. Besides that it's getting more polar as we're moving across, the molecular weights are essentially not changing. Notice they're very similar to each other. All right. Now also the shapes are very similar. So what this tells us is that because the molecular weights are very similar, and this is really important, guys, because the molecular weights are essentially the same, and the shapes are essentially the same, the dispersion forces here on all of these molecules are essentially equal to each other. So any differences in the boiling points are going to be due to the fact of the dipole, essentially. The dipole getting bigger and stronger. All right. So you can see that the boiling point for propane is less, just slightly less than the boiling point of dimethyl ether. And then the boiling point is just increasing as it's getting more and more polar. So the bottom line, what we learn from this here, and this is what you got to take away, this take-home message here, is that if you have molecules that have similar molecular weights and shapes, the boiling point will influence, or factor here, will be based on its polarity. The more polar a molecule is, the stronger the the larger the boiling point will be. All right, so here's our summary then. For molecules of approximately equal mass and size, the strength of the intermolecular attractions increase with increasing polarity. This will result in an increase in the boiling points of these molecules. And really, again, I think this right here, little statement, is going to be absolutely important in your notes. So when the molecules of two substances have comparable molecular weights and shapes, the dispersion forces are approximately equal in the two substances. Okay, that's important. All right, so let's look at kind of this final idea. Now, I can't stress the importance of this graph. In fact, I would go to as far as saying that you should be able to almost sketch out this graph that we're about to look at. Okay? So before we get into this graph, I want to summarize again some important points. It appears that molecular weight so far is the most important thing to determine the boiling points and melting points of substances. The higher the molecular weight, the more dispersion forces, the higher the boiling point. Second to that would be the shape, because the more surface area, the more dispersion forces, therefore the higher the boiling point. So we can think of molecular weight and shape both increasing or changing the dispersion forces. So dispersion forces have a big dominant factor in the boiling points and melting points of molecules. All right. However, hydrogen bonding is also going to have a big impact as well. Okay, and so when we look at this this graph here, for instance, let's look at group 14. This is the group 14 we see on the periodic table. And what we're going to do is take each element in group 14, and they're going to be bonded to 4 hydrogens. So essentially, if we look at this, we have CH4, we have SiH4, GeH4, and SnH4. All right. So in general, all of these elements that are bonded to 4 hydrogens are all going to have the same tetrahedral shape. All right. And in generally, if you look at these, they're all nonpolar. So these are all nonpolar. Okay. And so the question is then, if these are nonpolar, what's going to be the most governing influence of their boiling points? Well, you can see that as the molecular weight increases, so does generally the boiling point is increasing. So again, we see that the boiling point and molecular weight has a direct influence here on this group of elements. All right. But let's look at group 16 right here. Now group 16 contains, if you look at your periodic table, contains oxygen, sulfur, selenium, and tellurium. Now you will notice that all of our molecules here have those elements in it. They're all bonded to two hydrogens actually. All of these molecules, water, H2S, H2SE, and H2TE, all have the same molecular shape, and that is bent. They're all bent. The other thing is they all have permanent dipoles as well. Right? Their molecular weights are going to increase. All right, going from oxygen to tellurium. The question that I have for you is, notice that the graph shape, you start with oxygen way up here, the high boiling point, and then it drops, and then you get a gradual increase here. Now, is this the trend that we would expect to see? The answer should be no. You should actually see, if it's going up by molecular weight, that you should see if water should be way down here, and there should be an increase up here by molecular weight. So as the molecular weight increases, we should see the boiling point, much like we see with group 14. But we don't see that trend at all. Instead, we see that oxygen, or that's in water, has a much, in other words, water has a much higher boiling point than the rest of these. Okay? So the question is why does water have such a high boiling point than H2S and H2SE and H2TE if it has such a low molecular weight? And the key to water is it hydrogen bonds, if you haven't already guessed that yet. So because water hydrogen bonds, it's going to have a super high boiling point. So it appears that hydrogen bonding has a bigger influence than dispersion forces do, or what we say molecular weight. But as soon as we get to H2S, and even though these are polar molecules, H2S and H2SE and H2TE, they do not form hydrogen bonds. Therefore, dispersion forces take over, and the boiling point increases by increasing molecular weight. And we see our general trend there. All right, now we can see that with most of these other groups. So I'm going to erase this here and look at some of these other groups here. So, for instance, HF is going to have a lower molecular weight than HCl, but yet HF has a higher boiling point than HCl. Why? Because HF hydrogen bonds. It's the same thing with NH3. Ammonia has a much higher boiling point than PH3 because ammonia, NH3, will hydrogen bond, whereas PH3 will not. Okay, and so again, you can see the hydrogen bonding has a pretty critical impact on the boiling point, even more so than in the increase in molecular weight. All right, so I hope this makes sense to you. You may need to re-look at all of this lecture video and really study your notes on this. This area is really tough for students, being able to take a molecule and be able to compare 2 or 3 or 4 molecules and decide which one has a higher boiling point. But you have to use these principles to help you out. My last statement I was going to do. Okay, so this last statement, please put in your notes. Study it well. It's pretty important. So, when the molecules of 2 different substances differ widely in molecular weights and there is no hydrogen bonding, dispersion forces tend to determine which substance has the stronger intermolecular forces. So, what is all saying is that hydrogen bonding is the biggest influence. Next comes the dispersion forces. The more dispersion forces there are, the higher the molecular weight. And then finally, the dipole is going to have the factors. All right, kind of in that order, okay, at least for molecules. So to summarize everything then, what we find going back to the beginning is that covalent network solids have the highest boiling and melting points. Then metallic bonds, then ionic bonds, and then followed by molecules. Molecules are last in line with boiling points and melting points. However, we have to look at the intermolecular forces within a molecule. That's going to help us to determine which molecules have higher boiling points and melting points. And again, hydrogen bonding is the first big factor, followed by the number of dispersion forces, and then finally the dipole. All right, so that is it for this lecture video. Please study your notes very carefully to prepare for the quiz on this material and be prepared to answer any questions that you might have. Okay, so that is it for this video.